We often look up at the stars and wonder when they will arrive, when the first signal will come, when the first ship will land. We have spent decades pointing radio dishes at the sky, listening for a whisper, a hum, anything at all from the darkness above. And we wait. We wait because we believe that the universe is big enough, old enough, and strange enough that someone out there must be looking back at us. But what if the answer is not about who is out there? What if the real question, the harder question, is whether anyone could ever get here at all? Because the laws of our universe, the ones we can measure, the ones we can test, the ones that hold everything together, they suggest something far lonelier than we expected. It is physically and mathematically impossible for aliens to ever reach Earth. Now, that might sound like a bold claim. It might sound like something a person says when they have given up hope. But this is not about giving up. This is about understanding the rules, the deep, unbreakable rules that the universe wrote for itself long before our planet even existed. Rules that apply to every civilization, no matter how old, no matter how clever, no matter how desperate to cross the void. Think of it this way. Imagine the universe is an ocean, a dark, freezing ocean that stretches in every direction farther than any mind can picture. And scattered across that ocean are tiny islands. Some of them glow with the light of stars. Some of them might even hold life. But the ocean between them is not just wide, it is growing. Every second, the water between the islands is rising, pushing them further and further apart. And no boat, no matter how fast, no matter how well built, can cross that water before it becomes too wide to ever reach the other shore. That is our universe. Not a playground of connected worlds, not a neighborhood of friendly stars, but a collection of lonely islands separated by an abyss that is getting deeper with every passing moment. And the thing about this abyss is that it does not care how advanced you are. It does not care if you have figured out how to split the atom or how to harvest the light of a star. The rules are the same for everyone. So tonight, let us take a slow walk through the reasons why. Let us look at the physics, the biology, the math, and the silence. And by the end, I think you will see the universe in a new way. Not as a place of missed connections, but as something far more beautiful and far more fragile than we ever imagined. Let us start with the most fundamental rule in all of physics. It is not a suggestion. It is not a guideline. It is an iron law that has never been broken in the entire history of science. Nothing in the universe can travel faster than light. Now, you have probably heard that before. You have probably nodded along and thought, yes, light is fast. Things cannot go faster than it, and moved on. But the truth of this rule is deeper than most people realize, and it is the first and most important reason why aliens will never reach our doorstep. The speed of light is roughly 300 million meters per second. That is fast enough to circle the Earth 7.5 times in a single heartbeat. It is fast enough to reach the moon in about 1.25 seconds. It seems, on the surface, like it should be more than enough to get around the universe. But the universe is not built on human scales. And when you zoom out, light starts to look incredibly, painfully slow. The nearest star to our sun, a small red ember called Proxima Centauri, is about 4.25 light years away. That means that a beam of light, traveling at the fastest speed anything can possibly move in this universe, would take more than 4 years to get there. Not 4 hours, not 4 days, 4 years. And that is the closest star, the nearest one, the one sitting right on our doorstep in cosmic terms. But here is what makes this truly impossible. not just difficult. The speed of light is not really about light at all. Physicists sometimes call it the speed of causality. It is the speed at which any cause can produce any effect anywhere in the universe. It is the speed at which information, matter, energy, or influence of any kind can travel through the fabric of space and time. Light just happens to travel at that speed because photons have no mass. But the limit itself is woven into the structure of reality. When Albert Einstein published his special theory of relativity in 1905, he showed something that changed everything. He showed that as any object with mass moves faster and faster, it gets heavier. Not a little heavier, dramatically heavier. As you approach the speed of light, your mass climbs toward infinity. And to push something with infinite mass, you would need infinite energy, which means it is not just hard to reach the speed of light. It is mathematically impossible for anything with mass to reach it, let alone surpass it. Think about what that means for a spaceship. A real, physical spaceship made of metal and fuel and maybe even living beings. To accelerate that ship to 90% of the speed of light would require an almost unimaginable amount of energy. To push it to 99% would require exponentially more, and to reach 100% would require all the energy in the universe, literally all of it, and even then, it would not be enough. This is not a technology problem. It is not something that a more advanced civilization, tired of waking up at 3 a.m. because your sleep video ended. Cosmic Drifts Beyond the Stars plays for hours. No ads, no interruptions, no reaching for your phone. 5 full night sleep experiences, one-time purchase. Begin now at mycosmicdrift.com. Could engineer around with better engines or smarter computers. This is a feature of the universe itself. The rules of special relativity have been tested thousands of times in particle accelerators, in satellite experiments, in the behavior of cosmic rays, and in the ticking of atomic clocks. They have never failed, not once. Every time scientists at places like CERN smash particles together at nearly the speed of light, they watch exactly what Einstein predicted. The particles get more massive. They resist acceleration. Their clocks slow down. The universe bends itself to enforce this rule, and no particle, no wave, no signal of any kind has ever been observed to break it. Now, some people hear this and they think about science fiction. They think about warp drives and wormholes and hyperspace. And these are wonderful ideas. They make for great stories. But when you look at the actual physics behind them, every single one of them requires something that has never been observed and may not even be possible. Warp drives, for example, were proposed in a paper by a physicist named Miguel Alcubierre. The idea is elegant. Instead of moving the ship through space, you compress the space in front of the ship and expand the space behind it. The ship itself sits still in a bubble, and the bubble moves. It is a clever way to work around the speed limit, because technically, the ship is not moving faster than light. Space itself is being rearranged around it. But to actually build one, you would need something called exotic matter. This is matter with negative mass and negative energy density. No one has ever detected exotic matter. No experiment has ever produced it. No theory has shown it to be stable. And even if you could find some, the amount you would need is staggering. Early calculations suggested you would need more energy than exists in the observable universe. Later refinements brought that number down, but it remains in the realm of fantasy. A beautiful, mathematically interesting fantasy, but a fantasy all the same. Wormholes are in the same category. The idea of a shortcut through space, a tunnel connecting two distant points, comes directly from the equations of general relativity. The math allows them. But allowing something and making it real are two very different things. To keep a wormhole open, you would again need exotic matter. And even if you could keep one open, there is no known way to control where it leads, how big it is, or how long it lasts. Some physicists have argued that even approaching a wormhole would cause it to collapse instantly. It is a bit like looking at a map and drawing a straight line between two cities that are separated by a mountain range. On paper, the straight line is shorter. But in reality, there is no road through the mountain, and there may never be one. The line on the map is not a path, it is just a line. So we are left with the speed of light as a hard ceiling, not a soft one, not one that clever engineering can break through. A ceiling built into the architecture of the universe itself. And under that ceiling, the distances between stars are not just large, they are punishing. Let us put some numbers to this. Our fastest spacecraft, a probe called Voyage 1, has been traveling through space since 1977. It is moving at about 17 kilometers per second. That is roughly 38,000 miles per hour. It is the fastest human-made object to ever leave our solar system. And at that speed, it would take roughly 75,000 years to reach Proxima Centauri. 75,000 years. That is longer than the entirety of recorded human history. Longer than the time since the last ice age. Longer than the time since humans first painted on cave walls. And Proxima Centauri is next door. It is the closest star, the nearest light in the window. Beyond it, the distances only grow. The nearest star that might have a habitable planet is many light years further. The nearest galaxy, Andromeda, is 2.5 million light years away. The edge of the observable universe is 46 billion light years in every direction. These are not distances that patience can solve. These are distances that physics says may be forever uncrossable by any physical object. Because even if you could build a ship that traveled at a significant fraction of the speed of light, say 10%, the trip to the nearest star would still take over 40 years. A round trip would take nearly a century. And that is if everything goes perfectly. No breakdowns, no accidents, no running out of fuel. No unforeseen dangers in the interstellar void. And we have not even talked about what happens to the travelers during that time. We have not talked about the radiation, the isolation, the biology of trying to keep a living thing alive for decades or centuries in the emptiness between stars. But we will get there. For now, let us stay with the physics. Because the speed of light is only the beginning of the problem. There is another rule, equally iron, equally unforgiving, and it is one that most people have never heard of. It is the rule that the universe is not just big, it is getting bigger, and it is getting bigger faster than we ever expected. In 1929, an astronomer named Edwin Hubble made one of the most important discoveries in the history of science. He found that nearly every galaxy in the sky is moving away from us. And the further away a galaxy is, the faster it is moving. This was not because we are at the center of some cosmic explosion. It was because the space itself, the actual fabric of the universe, is stretching. Imagine drawing dots on a balloon and then inflating it. Every dot moves away from every other dot. Not because the dots are moving through the balloon, but because the balloon itself is expanding. This expansion is measured by something called the Hubble constant, and right now, its best measured value is about 73 kilometers per second per megaparsec. That is a mouthful, so let me translate. For every 3.25 million light years of distance between us and another galaxy, that galaxy is moving away from us at an additional 73 kilometers per second. The further away something is, the faster it recedes. And here is where it gets truly humbling. At a certain distance from Earth, roughly 14 billion light years, the expansion of space causes galaxies to recede from us faster than the speed of light. Now, this does not violate Einstein's rules, because the galaxies themselves are not moving through space faster than light. Space itself is stretching between us and them, and there is no speed limit on the stretching of space. But the effect is the same. Light from those galaxies, light that is already on its way to us, will never arrive. It has been running toward us since the beginning of the universe, and it will never make it, because the space it has to cross is growing faster than it can traverse it. This creates something called the cosmic event horizon. It is an invisible boundary around the Earth, around every point in the universe actually, beyond which events are forever hidden from us, not because we lack the technology to see them, not because we are not looking hard enough, but because the light from those events, traveling at the fastest speed in the universe, will never reach us, ever, in all of eternity. And it gets worse, because the expansion of the universe is not just happening, it is accelerating. In 1998, two teams of scientists made a discovery that earned them the Nobel Prize. They found that distant supernovae were dimmer than expected, which meant they were further away than expected, which meant the universe was expanding faster than expected. Something was pushing the cosmos apart, and it was getting stronger over time. That something is called dark energy. We do not know what it is. We cannot see it. We cannot touch it. We cannot capture it in a laboratory, but it makes up roughly 68% of everything that exists, and its effect is simple and devastating. It is pushing every galaxy away from every other galaxy, and it is doing so at an ever-increasing rate. Because of dark energy, the cosmic event horizon is not just a fixed boundary. It is closing in. Galaxies that we can see today, galaxies whose light has already reached us, are slipping beyond that horizon one by one. Every year, roughly 160 billion stars, spread across countless galaxies, pass beyond the event horizon and become forever unreachable. Not just unvisitable, unreachable by any signal, any light, any influence of any kind. Right now, scientists estimate that about 94% of all the galaxies in the observable universe are already beyond our reach. We can still see their light, because that light was emitted long ago, when they were closer. But if we sent a signal to them right now, traveling at the speed of light, it would never arrive, and they could never send one back. We are looking at ghosts, beautiful, ancient ghosts, and every day there are more of them. Think about what this means for the idea of interstellar contact. Even if there were a civilization out there, 1 billion years ahead of us, with technology we cannot even dream of, they would still be subject to this same expansion. They would still be trapped behind the same cosmic event horizon. They could not send a ship to us if we are on the other side of it. They could not send a signal. They could not even see us. The universe has drawn a curtain between us, and that curtain is getting thicker every second. And it is not just the distant galaxies that are affected. Even within our own observable universe, the expansion is making everything harder. The further away a star is, the more the light from that star gets stretched as it travels to us. This stretching is called redshift, and it makes distant objects dimmer, harder to detect, and eventually invisible. Over enormous timescales, the expansion of the universe will push every galaxy in the sky beyond our ability to observe it. In the very far future, trillions of years from now, an astronomer looking up from Earth or wherever our descendants might be, would see nothing. No galaxies, no distant stars, just a local group, our little island of galaxies, floating alone in an endless, empty darkness. The universe is not just big, it is big and getting bigger. And that simple fact creates a prison that no civilization, no matter how powerful, can escape. But let us stay here for a moment longer, because the expanding universe has another trick up its sleeve, one that makes the problem of interstellar travel not just difficult, but deeply, existentially isolating. When we talk about the expansion of space, we are not talking about something far away and irrelevant. We are talking about the fundamental nature of the ground beneath your feet, the air around you, the light from the screen you might be looking at right now. Space itself, the thing that separates you from the chair across the room, is the same fabric that separates us from Andromeda, and that fabric is stretching. It has been stretching since the Big Bang, roughly 13.8 billion years ago. In the early universe, right after the initial expansion, things were incredibly close together. Matter was dense and hot, and the distances between what would become galaxies were tiny compared to what they are now. But the universe kept expanding. Gravity tried to pull things back together, and for a long time, it did a decent job. The expansion slowed, galaxies formed, stars lit up, planets coalesced from dust and gas. Life, at least here on Earth, found a way. But then something changed. About 6 billion years ago, give or take, the expansion stopped slowing down and started speeding up. Dark energy, whatever it is, took the wheel. And since then, the distances between galaxies have been growing faster and faster. Not just growing, accelerating. The universe went from a slow drift to a sprint, and it shows no signs of stopping. This acceleration is what creates the event horizon we talked about, but it also creates something even more troubling for anyone dreaming of interstellar travel. It creates a sense of urgency, because every day that passes, the universe becomes a slightly lonelier place. The number of reachable galaxies shrinks. The number of stars we could theoretically visit, even at the speed of light, gets smaller. We are living in a window, a brief cosmic window, where we can still see the evidence of a universe that was once connected. But that window is closing, and when it closes, it does not open again. Some cosmologists have estimated that the cosmic event horizon currently sits about 16 billion light-years away from us. Beyond that distance, nothing we do can ever reach anything out there, and nothing out there can ever reach us. And because of the acceleration, that boundary will continue to shrink relative to what we can see. In the far future, the only things left within our reach will be the galaxies in our local group, the Milky Way, Andromeda, and a handful of smaller companions, all bound together by their mutual gravity. Everything else will have faded, redshifted into nothing, stretched into silence. Now, let me be clear. This does not mean those other galaxies stop existing. They are still out there. They are still full of stars and possibly civilizations. But they are on the other side of a horizon that might as well be a wall. A wall made not of stone or steel, but of expanding space. And no amount of technology, no amount of energy, no amount of time can breach it, because the wall itself is the universe. You cannot build a door in a wall that is made of everything. This is what I mean when I say the universe is not a playground. It is a collection of islands in a rising ocean, and the tide is coming in. So let us take stock. We have two enormous problems already. The speed of light puts a hard ceiling on how fast anything can travel, and the expansion of the universe puts a hard ceiling on how far anything can reach. Together, they create a cosmic prison, one that applies to us, to any aliens that might exist, and to every civilization that has ever arisen or ever will arise anywhere in the universe. But we are not done. Because even if you could somehow travel at a significant fraction of the speed of light, even if the expansion were not an issue, you would still face a problem that is much closer to home. A problem not of physics, but of biology. The human body, and really any biological body we can imagine, was not built for the emptiness between the stars. We evolved on a planet with a thick atmosphere, a strong magnetic field, a comfortable temperature range, and a gravity that our bones and muscles and hearts are perfectly calibrated to work within. Take any of those things away, and the body starts to fall apart. Take all of them away, which is exactly what happens in deep space, and you are looking at a slow-motion catastrophe. Let us start with the most immediate threat. Radiation. Space is full of it. Not the kind of radiation you get from a dental X-ray or a cell phone. The kind that comes screaming out of exploding stars. The kind that has been accelerated to nearly the speed of light by the shock waves of supernovae. The kind that carries enough energy to tear through metal, punch through the walls of a spacecraft, and shatter the strands of your DNA like a bullet through a spiderweb. These are called galactic cosmic rays, and they are one of the most dangerous things in the universe for any living thing trying to travel between stars. They are made up mostly of protons, the nuclei of hydrogen atoms, but about 12% are helium nuclei, and a small but deadly fraction are the nuclei of heavier elements like iron and carbon, stripped of their electrons and moving at nearly the speed of light. When one of these particles hits a living cell, it does not just pass through like an X-ray. It tears a path of destruction through the tissue, breaking chemical bonds, creating showers of secondary particles, and leaving behind a trail of damaged molecules that the cell may never be able to repair. A single heavy ion from a cosmic ray can damage multiple cells along its path. And in the deep space between stars, outside the protective bubble of any solar system, the bombardment is constant. On Earth, we are protected. Our planet's magnetic field acts like an invisible shield, deflecting most charged particles away from the surface. Our atmosphere adds another layer of protection, absorbing the energy of particles that do make it through. Astronauts on the International Space Station are partially protected because they are still within the Earth's magnetic field, although they receive significantly more radiation than people on the ground. But once you leave that protective bubble, once you venture out into interstellar space, the shielding is gone. NASA has estimated that astronauts on a round trip to Mars, which is only a few months in each direction, would receive radiation doses in the range of 50 to 2,000 millisieverts. To put that in perspective, 1 millisievert is roughly equivalent to 10 chest X-rays. 2,000 millisieverts is enough to cause measurable increases in cancer risk, damage to the central nervous system, weakening of the immune system, and degenerative diseases. And that is for a trip to Mars. A trip to the nearest star, even at 10% of the speed of light, would take over 40 years. The cumulative radiation dose over that time would be catastrophic. And here is the thing that makes this even harder. You cannot just build thicker walls. Conventional shielding, the kind made of aluminum or steel, actually makes the problem worse in some cases. When a high-energy cosmic ray hits a piece of metal, it does not just stop. It shatters the atomic nuclei in the metal, creating a spray of secondary particles, neutrons, protons, lighter nuclei, and gamma rays that can be even more biologically damaging than the original particle. This is called a nuclear spallation cascade, and it means that thin shielding can actually increase the radiation dose inside a spacecraft rather than decrease it. To get meaningful protection, you would need either incredibly thick layers of material, which would make the spacecraft impossibly heavy, or you would need to use materials like water or polyethylene that are rich in hydrogen atoms, which are better at absorbing cosmic rays without producing as many secondary particles. But even with the best materials, the shielding would need to be meters thick to reduce the dose to acceptable levels. And carrying that much mass on an interstellar voyage is impractical with any propulsion system we can currently imagine. Some scientists have proposed active shielding, using powerful electromagnetic fields to deflect charged particles the way the Earth's magnetic field does. This is a promising idea, but the engineering challenges are enormous. You would need superconducting magnets of extraordinary strength running continuously for decades, powered by a reliable energy source in the vacuum and cold of deep space. The technology does not exist today, and even if it did, it is not clear that it could handle the highest energy cosmic rays, which carry so much momentum that even strong magnetic fields would barely bend their paths. And then there is the Sun. Our own star regularly throws out enormous bursts of radiation called solar particle events. These are less energetic than galactic cosmic rays, but they come in sudden, intense storms that can deliver a potentially lethal dose in a matter of hours. On a ship between the stars, there would be no solar storms, but there would be no warning system either. A nearby star could flare, and the crew would have no time to shelter. So radiation is a killer. A slow, invisible, relentless killer that gets worse the longer you spend in space and the further you are from the protection of a planet. For a trip lasting decades or centuries, the biological damage would accumulate year after year, with no way to repair it faster than it is being caused. But radiation is not the only biological challenge. There is also the problem of gravity, or rather, the lack of it. Every cell in your body, every bone, every muscle, every drop of blood was designed to work under the constant pull of Earth's gravity. We do not think about it because it is always there, like the air we breathe. But take it away, and the body begins to betray you. In microgravity, the kind of weightlessness that astronauts experience on the International Space Station, the changes start within days. Fluid that normally pools in your legs under gravity redistributes throughout your body. Your face puffs up. Your sinuses become congested. The pressure inside your skull increases, which can push on your optic nerves and damage your eyesight. Some astronauts have returned from long missions with permanent changes to their vision, but the most serious effects are on your bones and muscles. On Earth, your skeleton is constantly being remodeled. Old bone is broken down by cells called osteoclasts, and new bone is built up by cells called osteoblasts. This process is driven, in part, by the mechanical stress that gravity places on your bones. Every step you take, every time you stand up, every time you lift something, your bones are being told to stay strong. In microgravity, that signal disappears. The osteoblasts slow down. The osteoclasts keep working, and the result is a steady, measurable loss of bone density. Astronauts on the space station lose roughly 1 to 2% of their bone mass per month, concentrated in the weight-bearing bones of the hips and legs. After 6 months, some astronauts show bone loss comparable to what a person with severe osteoporosis might experience over a decade on Earth. And while exercise can slow this loss, it cannot stop it entirely. Even with 2 hours of vigorous exercise every day, using specially designed resistance machines, astronauts still come home with measurably weaker skeletons. The muscles tell a similar story. Without gravity to work against, the muscles of the legs and back begin to atrophy. Slow-twitch muscle fibers, the ones used for standing and walking and maintaining posture, are replaced by fast, twitch fibers that are less useful for sustained effort. Astronauts can lose up to 20% of their muscle mass in as little as 2 weeks without proper exercise. After months, the loss can be severe enough to compromise their ability to walk or perform basic physical tasks when they return to gravity. And here is the part that matters for interstellar travel. These effects do not plateau. They continue for as long as you remain in microgravity. After a few months, the rate of bone loss may slow slightly, but it does not stop. After a year, after 5 years, after a decade, the cumulative damage would be staggering. A person who spent 20 years in weightlessness would have a skeleton that could barely support them on a planet's surface. Their muscles would be shadows of what they once were. Their cardiovascular system would be weakened. Their immune system would be compromised. Some people suggest artificial gravity as a solution. Spin the ship, create centrifugal force, mimic the pull of a planet. And this is a reasonable idea in principle. But building a spacecraft large enough to spin at a rate that produces comfortable artificial gravity, without making the occupants dizzy from the Coriolis effect, is an enormous engineering challenge. The ship would need to be hundreds of meters across, which means much more mass, which means much more fuel, which brings us right back to the energy problem we already discussed. There is also the question of time. Not physical time, but biological time. The human lifespan, even under ideal conditions, is roughly 80 to 90 years. A trip to the nearest star at 10% of the speed of light would take more than 40 years one way. A round trip would consume an entire lifetime. And that is the nearest star. To reach anything interesting, anything where an alien civilization might exist, you would likely need to travel hundreds or thousands of light years, which means hundreds or thousands of years of travel time. You could put the crew in some kind of suspended animation, assuming that were possible. But cryogenics remains science fiction. No one has successfully frozen a complex organism, kept it that way for an extended period, and brought it back to life without severe tissue damage. The ice crystals that form inside cells during freezing tear apart the delicate structures that keep those cells alive. Some organisms, like certain species of frogs and tardigrades, can survive partial freezing, but they are simple compared to a human being, and they do not stay frozen for decades. You could build a generation ship, a vessel large enough to sustain a human population for centuries, with each generation passing the mission on to the next. This is a popular concept in science fiction, and it has a certain romantic appeal, but the practical challenges are immense. You would need a completely self-sustaining ecosystem, one that could produce food, recycle water and air, manage waste, and maintain itself for hundreds of years without any resupply from Earth. You would need a social structure that could survive the pressures of confinement, isolation, and the knowledge that none of the people on board would live to see the destination. You would need to solve every biological problem we have discussed: radiation, bone loss, muscle atrophy, vision damage, and maintain a healthy, genetically diverse population for generations. And even then, even if you could build such a ship, you would arrive at your destination centuries later to find a universe that has moved on without you. The stars you were aiming for would have drifted. The planets would have changed. Any civilization that might have been there when you left could be long gone by the time you arrived. The biology of time is a wall. not as dramatic as the speed of light or the expansion of space, but just as real and just as unforgiving. Living things have clocks. They age, they break down, they die. And the distances between stars are measured not in miles, but in lifetimes. So let us add this to our list. The speed of light says you cannot go fast enough. The expansion of the universe says you cannot reach far enough. And biology says you cannot survive long enough. 3 walls, all converging on the same answer. The stars are out of reach. But there is one more wall to consider. And in some ways, it is the most sobering of all. It is the wall of energy. Not just the energy needed to go fast, which we already discussed, but the total energy budget that any civilization, anywhere in the universe, has to work with. To move anything through space, you need energy. The heavier the thing is, the more energy you need. The faster you want it to go, the more energy you need. And for interstellar travel, the amounts are not just large. They are absurd. Let us do some simple math. Imagine a spacecraft with a mass of about 100,000 kilograms, roughly the mass of a large commercial airplane. Now imagine we want to accelerate that spacecraft to 10% of the speed of light, about 30 million meters per second. Using the basic kinetic energy formula, the energy required is about 4.5 times 10 to the 19th joules. That is 4.5 followed by 19 zeros. For perspective, that is roughly the total energy output of the entire United States for an entire year. For one ship, for one trip, at only 10% of light speed. And that calculation is absurdly optimistic because it does not account for the mass of the fuel. In any rocket, you have to carry the fuel that will be used for acceleration. But that fuel has mass, which means you need more fuel to carry that fuel, which means you need more fuel to carry that fuel. This is called the tyranny of the rocket equation, and it is one of the most fundamental challenges in rocketry. For chemical rockets, the kind we use today, the amount of fuel needed for interstellar travel would be so vast that it would dwarf the ship itself by orders of magnitude. Even with nuclear propulsion, the numbers are daunting. A nuclear thermal rocket, which heats hydrogen fuel using a fission reactor, is about twice as efficient as a chemical rocket, but twice as efficient is still nowhere near enough. A nuclear pulse drive, which detonates small nuclear bombs behind the ship to push it forward, is more promising. Freeman Dyson calculated that a ship using this method could theoretically reach about 8 to 10% of the speed of light. But the amount of nuclear fuel required would be measured in hundreds of thousands of tons, and the engineering challenges of surviving repeated nuclear detonations are, to put it mildly, significant. The most efficient propulsion system anyone has conceived is a matter-antimatter annihilation engine. When matter meets antimatter, 100% of both masses are converted directly into energy, as described by Einstein's famous equation. This is the most efficient energy conversion process known to physics, but antimatter is extraordinarily difficult to produce. The total amount of antimatter ever created in all the particle accelerators on Earth is measured in nanograms. To produce enough for an interstellar trip would require more energy than our civilization currently generates by a wide margin. And storing it is another problem entirely, since antimatter annihilates on contact with any normal matter, including the walls of whatever container you put it in. This brings us to a concept developed by a Soviet astronomer named Nikolai Kardashev in 1964. The Kardashev scale is a way of categorizing civilizations by the total amount of energy they can harness and use. A Type 1 civilization can harness and use all the energy that falls on its home planet from its parent star. For Earth, that is about 10 to the power of 17 watts. Humanity is not even there yet. We are currently estimated to be at about 0.73 on the scale, meaning we use a fraction of the energy available to us on our own planet. A Type 2 civilization can harness the entire energy output of its star. For our Sun, that is about 10 to the power of 26 watts. This would require something like a Dyson sphere, a hypothetical structure that completely surrounds a star and captures all of its light. No civilization has ever been observed to have built one, and the engineering challenges are beyond anything we can currently comprehend. A Type 3 civilization can harness the energy output of an entire galaxy, about 10 to the power of 36 watts. This represents a level of technology and coordination that is almost incomprehensible, a civilization that could control the energy of billions of stars. Now, here is the problem. Even a Type 2 civilization, one that has mastered the entire energy output of its star, would still struggle with interstellar travel. The energy requirements for moving a spacecraft at any significant fraction of the speed of light are so enormous that even stellar-scale energy production might not be enough. And for intergalactic travel, the energy needed would push you into Type 3 territory, a level that may be physically impossible to achieve given the distances and communication delays involved. Physicist Michio Kaku has pointed out that all of the theoretical proposals for faster-than-light travel, warp drives, wormholes, manipulation of extra dimensions, require energies that are characteristic of Type 3 civilizations or beyond. They require the ability to manipulate the very fabric of space-time, to generate and control exotic matter, to harness energies at the Planck scale, the scale at which gravity and quantum mechanics meet. These are not just engineering challenges. They are challenges at the frontier of fundamental physics, and we do not even know if they have solutions. So the energy wall is real. It is not a wall of not having enough fuel. It is a wall of the universe not having enough energy, at least not in a form that any civilization could practically harness and direct toward a single purpose, like crossing the void between stars. And now we come to what might be the most heartbreaking part of this whole story, because it is not just ships that cannot cross the void, even messages cannot. When we think about aliens, we often imagine receiving a signal, a radio transmission, a pattern of pulses, something that says, "We are here, we know you are there, you are not alone." It is the premise of countless stories and the entire mission of an organization called SETI, the Search for Extraterrestrial Intelligence. For decades, SETI has been pointing radio telescopes at the sky, scanning thousands of frequencies, listening for anything that does not sound natural, and they have heard nothing. Decades of listening, and the sky has been silent. Some people find this discouraging. Others find it mysterious. But when you understand the physics of signals traveling through interstellar space, the silence starts to make perfect sense. Because sending a message across the stars is not like sending an email or making a phone call. It is more like whispering into a hurricane and hoping someone on the other side of the world can hear you. The first problem is the inverse square law. This is one of the most basic rules in physics, and it applies to light, radio waves, gravity, and basically everything that radiates outward from a source. The rule says that the strength of a signal decreases with the square of the distance from the source. Double the distance, and the signal gets 4 times weaker. Triple the distance, and it gets 9 times weaker. Go 10 times further, and the signal is 100 times weaker. For radio signals traveling across interstellar distances, this law is devastating. A signal that is perfectly clear at a distance of 1 light year would be more than 16 times weaker at 4 light years. At 100 light years, it would be 10,000 times weaker. At 1,000 light years, it would be 1,000,000 times weaker. And the distances in our galaxy are measured in tens of thousands of light years. To illustrate how severe this is, consider Voyager 1. It is the most distant human-made object, currently about 163 astronomical units from Earth. That is a tiny distance in interstellar terms. And yet, the signal that Voyager sends back to us is so faint that the power reaching our antennas is about 20 billionths the power of a watch battery. We can only detect it because we know exactly where to point our antennas. We know exactly what frequency to listen on, and we use some of the most sensitive receivers ever built. Now imagine trying to detect a similar signal from a civilization around another star, 4 light years away. That star is about 17,000 times further than Voyager. Because of the inverse square law, the signal would be about 300 million times weaker. To detect something that faint, you would need either an extraordinarily powerful transmitter on the other end, something broadcasting with the energy of millions of watts focused in a tight beam, aimed directly at Earth. Or you would need a receiver on our end that is far more sensitive than anything we currently possess. And that assumes the signal is aimed at us. If the civilization is broadcasting in all directions, like our own television and radio signals, the power is spread across the surface of an ever-expanding sphere. By the time that sphere reaches the nearest star, the signal is spread so thin that it is indistinguishable from the background noise of the cosmos. Our own radio and television broadcasts, the ones that have been leaking into space since the 1930s, are already undetectable beyond a distance of about 1 or 2 light years. They do not even make it to the nearest star. They simply fade into static, overwhelmed by the natural radio emissions of the galaxy. But the inverse square law is not the only problem. The interstellar medium, the gas and dust that fills the space between stars, also degrades signals. Radio waves passing through this medium experience something called dispersion, where different frequencies arrive at slightly different times, smearing the signal out and making it harder to decode. There is also scattering, where tiny particles deflect the waves slightly, further weakening and distorting them. And there is absorption, where certain frequencies are partially blocked by atoms and molecules in the interstellar gas. Over short distances, these effects are small, but over thousands of light years, they can be significant. A signal that starts as a crisp, clear pattern of ones and zeros can arrive as a faint, smeared, noisy mess that is nearly impossible to distinguish from the natural background. Even if an alien civilization were broadcasting a powerful, focused signal directly at us from across the galaxy, the interstellar medium would have decades or centuries to degrade it before it reached our receivers. And then there is the question of time. Radio waves travel at the speed of light. A signal sent from a star 1,000 light years away would take 1,000 years to reach us. If we detected it and wanted to respond, our reply would take another 1,000 years to get back. A simple conversation, a basic exchange of information, would take 2,000 years. By the time our response arrived, the civilization that sent the original message might no longer exist. They might have gone extinct, evolved beyond recognition, or simply moved on to other concerns. This is not communication. This is archaeology. We would not be talking to aliens. We would be finding their fossils, their echoes, the lingering traces of something that happened long ago and far away. Some scientists have proposed alternative methods of communication, Laser signals, for example, are much more focused than radio waves and could in theory carry more information over longer distances with less spreading. But they are also much harder to detect because you have to be looking in exactly the right direction at exactly the right time, and they still travel at the speed of light, so the time delay problem remains. Others have suggested using neutrinos or gravitational waves as communication carriers. These have the advantage of passing through most matter without being absorbed or scattered. But they are extraordinarily difficult to generate in a controlled way and even more difficult to detect. Current neutrino detectors require massive underground facilities and can only capture a handful of neutrinos from the Sun, which is right next door. Detecting a neutrino signal from another star system would require technology that is currently beyond our imagination. The silence of the sky is not evidence that we are alone. It is evidence that the universe is very, very good at keeping its inhabitants apart. Even if the galaxy were teeming with intelligent civilizations, all of them broadcasting, all of them eager to make contact, the vast majority of their signals would never reach us. They would be swallowed by distance, scattered by dust, smeared by dispersion, and lost in the noise. We often forget that. We look at the night sky and see a canvas of possibility. But what we are really seeing is a canvas of separation. Every star is an island. Every planet is a grain of sand on that island. And the ocean between them is so wide, so deep, and so turbulent that even a message in a bottle cannot make the crossing. This brings us to one of the most famous puzzles in all of science. It is called the Fermi paradox, and it was born from a simple question asked by the physicist Enrico Fermi during a lunch conversation in 1950. He looked at the numbers, the billions of stars in our galaxy, the billions of years the galaxy has existed, the likelihood that at least some of those stars have planets, and at least some of those planets have life. And he asked a question that still haunts us. Where is everybody? The math says they should be out there. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. Many of those stars have planets. Some of those planets are in the habitable zone, the region where liquid water could exist on the surface. The galaxy is more than 13 billion years old, which means there has been plenty of time for civilizations to arise, develop technology, and spread across the stars. And yet, nothing. No signals, no visits, no artifacts, no megastructures blocking the light of distant stars, no evidence of any kind that anyone else is out there or has ever been out there. One of the most compelling explanations for this silence is an idea called the Great Filter. It was proposed by an economist named Robin Hanson in 1996, and it goes like this. Between the formation of a potentially habitable planet and the emergence of a civilization capable of colonizing its galaxy, there must be at least one step that is extraordinarily difficult, so difficult that almost no civilization, anywhere, at any time, has ever made it past. This step is the Great Filter. It is the wall that stops intelligent life from becoming a galactic presence. And the disturbing question is whether that wall is behind us or in front of us. If the Great Filter is behind us, then it is something that happened in our past. Maybe it is the origin of life itself, the transition from dead chemistry to living biology. We still do not fully understand how that happened, and it may be vanishingly rare. Maybe it is the leap from single-celled organisms to complex multicellular life, which took over 1 billion years on Earth. Maybe it is the development of intelligence, or tool use, or language, or science. Any one of these steps could be the bottleneck. And if it is, then the reason we do not see aliens is simple. They never got this far. But if the great filter is in front of us, then it is something that every civilization eventually faces and fails to survive. Maybe it is nuclear war. Maybe it is environmental collapse. Maybe it is artificial intelligence that goes wrong, or a pandemic that cannot be contained, or some other catastrophe that advanced civilizations inevitably create for themselves. In this scenario, the universe is littered with the ruins of civilizations that rose, thrived briefly, and then destroyed themselves before they could ever reach the stars. There is a third possibility, and it is the one that connects most directly to everything we have been talking about tonight. Maybe the great filter is not biological or social at all. Maybe it is physical. Maybe the filter is simply the universe itself. The distances, the energy requirements, the radiation, the expansion, the cold equations of physics that say no matter how smart you are, no matter how determined, you cannot cross the void. In this version of the great filter, civilizations do not destroy themselves. They thrive. They build great things on their home worlds and in their local star systems. They develop wonderful science and beautiful art and deep philosophies. But they never leave. Not because they do not want to. Not because they are afraid. But because the universe will not let them. They are born on their little islands. They look out at the ocean. They dream of other shores. And they live their entire lives, their entire histories, without ever knowing whether anyone is dreaming the same dream on the other side. This is, in many ways, the loneliest possible answer to the Fermi paradox. It does not require malice. It does not require stupidity. It does not require self-destruction. It just requires physics. The same physics that makes the stars shine and the planets spin and the atoms hold together. The same physics that makes everything beautiful also makes everything separate. Let us go deeper into this idea, because it is worth understanding just how universal these constraints really are. We sometimes imagine that an alien civilization 1,000,000 years ahead of us would have figured out solutions to all the problems we have discussed. And it is true that they would know more than we do. They would have better technology, better math, a deeper understanding of the universe. But understanding the rules and breaking the rules are two very different things. We understand gravity perfectly well, in the sense that we can predict its effects with extraordinary precision. But we cannot turn it off. We cannot make it go away. We cannot choose to ignore it. A civilization 1,000,000 years ahead of us would understand the speed of light even better than we do. They would have tested it in ways we cannot imagine. But that does not mean they could exceed it. Understanding a limit is not the same as transcending it. Consider this analogy. A fish in the deep ocean understands its environment intimately. It knows how to navigate the currents, how to find food, how to avoid predators. It has spent millions of years evolving to thrive in its world. But no amount of evolution, no amount of intelligence, no amount of technology developed by that fish could allow it to fly to the moon. The medium it lives in, the water, the pressure, the physics of its body, simply does not permit it. It is not a failure of the fish. It is a feature of its world. We may be in the same position. Our world is not just Earth. Our world is the universe, with all its rules and constraints. And those rules may simply not allow what we are dreaming of. Not because we are not smart enough, but because the dream itself is incompatible with the way reality works. This is a hard thing to accept. Humans are explorers by nature. We crossed oceans, we climbed mountains, we went to the moon. Every boundary we have ever encountered, we have pushed past. It feels wrong, almost offensive, to suggest that there might be a boundary we cannot cross. But the universe is under no obligation to be convenient. It is under no obligation to make our dreams come true. It simply is what it is. And what it is, in the cold light of physics, is a place where the islands are very far apart and the ocean is getting deeper. Now, I want to be careful here. I am not saying that science will never surprise us. Science has surprised us many times before. 100 years ago, the idea that the universe was expanding would have seemed absurd. 50 years ago, the idea that we could detect gravitational waves was a pipe dream. 20 years ago, the idea that we could photograph a black hole was laughable. The history of science is a history of things we thought were impossible turning out to be possible. But there is a difference between things that are hard and things that are forbidden. It was hard to detect gravitational waves, but physics allowed it. The waves were real, and the challenge was engineering. Faster than light travel is not just hard. It appears to be forbidden by the very structure of space-time. The challenge is not engineering. It is the laws of nature themselves. And while it is always possible that we are wrong about those laws, every experiment we have ever conducted says that we are right. If we are wrong, we will be delighted. We will throw a party. We will rewrite the textbooks and start building starships. But until that day comes, if it ever does, we have to deal with the universe as we find it. And the universe we find is one where the stars are beautiful and distant, and almost certainly unreachable. Let me tell you something about the nearest stars that most people do not realize. When you look up at the night sky and see the stars, you are not seeing them as they are. You are seeing them as they were. The light from Alpha Centauri, the nearest bright star system, takes about 4¼ years to reach your eyes. When you look at it, you are seeing it as it was 4¼ years ago. If something happened there tonight, you would not know about it until 2030 or so. The light from Sirius, the brightest star in the sky, takes about 8½ years to reach us. The light from Vega takes about 25 years. The light from Polaris, the North Star, takes about 400 years. When you look at Polaris, you are seeing it as it was when Shakespeare was writing his plays. And those are some of the closest stars. The light from the center of our galaxy takes about 26,000 years to reach us. The light from the Andromeda Galaxy takes about 2½ million years. The light from the most distant galaxies we can see has been traveling for over 13 billion years. This means that when we look at the universe, we are looking at the past. We are looking at history. We are seeing events that happened long ago, from places that may look very different now. And because of the expansion of the universe, many of the objects we see no longer exist in any form we could ever reach or interact with. They are images, recordings, echoes of a universe that has already changed. This is not just poetic. It has practical implications for the search for alien life. If we detected a signal from a star 1,000 light years away, that signal was sent 1,000 years ago. The civilization that sent it may no longer exist. They may have evolved. They may have destroyed themselves. They may have simply stopped transmitting. We would have no way of knowing. And if we sent a reply, it would take another 1,000 years to arrive, by which time everything would have changed again. The universe is not a place where conversations happen. It is a place where monologues echo across the void, growing fainter and fainter, until they dissolve into the background noise of creation. And this brings us to another dimension of the problem that we have not yet discussed. The dimension of time. Not the time it takes to travel, which we have already covered, but the time it takes for civilizations to arise, persist and fade. The universe is 13.8 billion years old. Life on Earth appeared roughly 3.8 billion years ago. Complex life, the kind with brains and eyes and limbs, appeared only about 500 million years ago. Human civilization, the kind that builds cities and writes books and sends radio signals, has existed for roughly 10,000 years. And the technological civilization that could, in principle, detect or send interstellar signals has existed for less than a century. That is an extraordinarily narrow window. In the 13.8 billion year history of the universe, our technological civilization has been present for about 0.01% of it. If there are other civilizations out there, the chances that they exist at the same time as us, in the same sliver of cosmic history, are extraordinarily small. This is called the temporal problem. Even if civilizations are common, they might be separated not just by space but by time. A civilization that flourished 2 billion years ago on the other side of the galaxy would have left no trace that we could detect. Their radio signals would have faded to nothing. Their light would show no sign of their presence. They would be as invisible to us as a campfire that burned out 10,000 years ago is invisible to someone walking through the forest today. And the universe does not preserve civilizations. Stars die, planets are swallowed, galaxies collide. Over billions of years, the cosmic landscape changes so completely that any trace of a past civilization would be erased by the sheer violence of natural processes. We look at the sky and see no evidence of alien life, and we wonder why. But perhaps the answer is not that they never existed. Perhaps the answer is that they came and went while we were still single-celled organisms floating in a warm ocean, unaware that anything else existed. The universe is patient. It has time. It has been here for 13.8 billion years, and it will continue for trillions more. Against that backdrop, the lifespan of a civilization is a flash, a spark in the darkness, beautiful and brief and easily missed. So let us sit with this for a moment. Let us really take in the full scope of what we are dealing with. The speed of light is a wall. The expansion of space is a closing door. Radiation is a slow poison. Microgravity is a thief stealing your bones and muscles. The energy requirements are beyond what even stellar-scale civilizations might command. Signals degrade into noise. Time separates us as surely as distance. And the great filter, whatever it is, may simply be the universe saying no. Each of these problems alone would make interstellar travel extraordinarily difficult. Together, they make it something close to impossible. Not impossible in the way that lifting a heavy rock is impossible, where you just need a bigger lever. Impossible in the way that a fish swimming to the moon is impossible, where the very laws of the medium forbid it. But I want to go further, because there are aspects of this problem that most people never consider. Things that go beyond the physics and into the very nature of what it means to exist as a physical being in a physical universe. Let us talk about the void itself. Not the void between stars, which we have already covered, but the void between galaxies. Because if interstellar travel is the hard problem, intergalactic travel is the impossible one. The Milky Way, our home galaxy, is about 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. Even at the speed of light, crossing it from one end to the other would take 100,000 years. That alone is a staggering number. But the Milky Way is just one galaxy among trillions. And the spaces between galaxies make the spaces between stars look like nothing. The nearest large galaxy to us is Andromeda, about 2.5 million light-years away. That is 25 times the diameter of our own galaxy. At the speed of light, it would take 2.5 million years to get there. At 10% of the speed of light, it would take 25 million years. At the speed of Voyager 1, it would take roughly 45 billion years, more than 3 times the current age of the universe. And Andromeda is close. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away. The nearest supercluster beyond our own, the Perseus-Pisces supercluster, is about 250 million light-years away. The observable universe stretches 46 billion light-years in every direction. These are not distances that any physical thing can cross. They are not distances that any amount of technology can bridge. They are distances that exist on a scale so far beyond anything in our experience that they might as well be infinite. When astronomers talk about the large-scale structure of the universe, they use words like filaments and voids and walls. The universe on the larger scales looks like a cosmic web, a network of thin threads of galaxies separated by enormous bubbles of nearly empty space. The voids between these filaments are hundreds of millions of light-years across. They contain almost nothing, just a few sparse atoms of hydrogen per cubic meter, and the ghostly remnants of the Big Bang. Crossing one of these voids would be like crossing an ocean with no islands, no landmarks, no currents to follow, and nothing to sustain you. Just emptiness, stretching in every direction, for hundreds of millions of years of travel. No civilization, no matter how advanced, could sustain a mission across such a void. The energy required would be beyond calculation. The time required would exceed the lifespan of most stars. The isolation would be absolute. And remember, these voids are not static. They are growing. The expansion of the universe is most pronounced in the emptiest regions of space, where there is the least matter to resist it. The voids between galaxy clusters are expanding faster than any spacecraft could cross them. They are growing not because anything is pushing them apart, but because the fabric of space itself is stretching. And you cannot outrun the stretching of space, because the stretching is happening everywhere, including in the space that your ship would be traveling through. This is what I mean when I talk about a cosmic prison. It is not a prison with bars. It is a prison without walls, a prison where the doors are open, but the corridors stretch to infinity in every direction, and the further you walk, the longer the corridors become. You are free to move in any direction you choose, but you will never arrive anywhere you have not already been. Let me give you another way to think about this. Imagine 2 ants on a balloon. They can walk in any direction on the surface of the balloon. They can even walk toward each other. But if the balloon is being inflated, and it is being inflated faster than the ants can walk, then no matter how hard they try, the distance between them will only increase. They might spend their entire lives walking toward each other and end up further apart than when they started. That is our universe. We are ants on an inflating balloon, and the rate of inflation is accelerating. Now, some people have pointed out that within our own galaxy, the expansion of space is negligible. Galaxies are held together by gravity, and within a galaxy, the distances between stars are not increasing due to cosmic expansion. This is true, and it means that, in principle, travel within the Milky Way is not affected by the expansion of the universe, but it is affected by everything else. The speed of light still applies. The energy requirements are still enormous. The radiation is still deadly. The biology is still fragile. And the distances, while smaller than intergalactic ones, are still immense. The Milky Way is 100,000 light-years across. Even at the speed of light, crossing it would take longer than our species has existed. At any realistic speed, it would take millions of years. And within that time, the galaxy itself would change. Stars would be born and die. Planets would shift in their orbits. The spiral arms of the galaxy would rotate. By the time a ship launched from one side of the galaxy arrived at the other, the destination would be unrecognizable. The stars it was aiming for might no longer exist. New stars would have taken their place. The cosmic landscape would be as different as the Earth was 1,000,000 years ago compared to today. This is the problem of scale. Not just the scale of space, which is hard enough, but the scale of time. Everything in the universe is moving, changing, evolving, dying, and being reborn. A journey that takes millions of years is not a journey through a static landscape. It is a journey through a moving target, a shifting maze that rearranges itself while you are trying to navigate it. Let me tell you about something called the cosmic microwave background. It is the oldest light in the universe, emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. This light has been traveling through space for over 13 billion years, and it fills the entire universe. It is everywhere. In every direction you look, at every frequency, this ancient light is streaming past you right now. When it was first emitted, it was hot and bright, the glow of a young, dense, fiery universe. But in the 13 billion years since, the expansion of space has stretched its wavelength by a factor of about 1,000. What was once visible light, the kind you can see with your eyes, is now microwave radiation, invisible and cold, with a temperature of just 2.7 degrees above absolute zero. This is what the expansion of the universe does to light. It stretches it. It cools it. It steals its energy, one wavelength at a time, until the light that once blazed across the cosmos is reduced to a faint, cold whisper. And what it does to light, it does to everything. Every signal, every beam, every photon that travels through expanding space loses energy as it goes. This is not because something is absorbing it. It is because the space itself is growing, and the light is being stretched along with it. This process is called cosmological redshift, and it is one of the most important observations in all of astronomy. It is how we know the universe is expanding. It is how we measure the distances to faraway galaxies. And it is one more reason why interstellar and intergalactic communication is so profoundly difficult. Any signal sent across vast distances of space will arrive redshifted, weakened, its energy diluted by the expansion of the cosmos. A powerful radio signal sent from a distant galaxy billions of years ago would arrive here as a whisper so faint that it would be indistinguishable from the cosmic microwave background itself. The universe has a built-in noise floor, a static hiss left over from its own birth, and any signal that has to travel far enough will eventually sink below that floor, lost forever in the cosmic background. It is a bit like trying to hear someone call your name from the other side of a waterfall. They might be shouting with everything they have, but the water is too loud, the distance is too great, and no matter how carefully you listen, the message is drowned before it reaches your ears. Let us now consider a thought experiment, a favorite exercise of physicists and dreamers alike. Let us imagine the most advanced civilization we can possibly conceive, not a civilization 100 years ahead of us, or 1,000 years, but a civilization 1 billion years ahead, a civilization that has had 1 billion years of uninterrupted scientific progress, 1 billion years to understand the universe, to develop technology, to solve problems that we cannot even formulate. What could such a civilization do? Well, they would certainly understand the speed of light. They would understand quantum mechanics and general relativity, and probably theories of physics that we have not yet imagined. They might have unified all the forces of nature into a single framework. They might understand the nature of dark matter and dark energy. They might have solved the mystery of consciousness. They might have achieved a harmony with their environment that makes our own civilization look like children playing with matches. But they would still be subject to the laws of physics. 1 billion years of progress does not change the speed of light. It does not change the expansion of the universe. It does not change the inverse square law, or the behavior of cosmic rays, or the relationship between energy and mass. These things are not cultural. They are not technological. They are structural features of reality itself. Such a civilization might have found ways to live more efficiently, to harness more energy, to extend their lifespans, to protect themselves from radiation. They might have migrated into the cores of their computers, becoming digital beings free from the constraints of biological bodies. They might have built megastructures around their stars, harvesting every photon of light. They might have colonized every habitable body in their solar system and engineered new habitats where none existed before. But they would still be in their solar system, or perhaps their local group of stars. They might have managed to send probes or even colony ships to nearby stars, crawling across the light years over millennia. But the idea that such a civilization could span a galaxy, let alone the universe, runs headlong into the same walls we have been discussing all night. Communication across a galaxy at the speed of light takes tens of thousands of years. Governing a galactic empire, coordinating activities across such distances, is not just difficult, it is physically meaningless. By the time a message from the galactic capital reaches the frontier, the situation it was responding to would be ancient history. By the time a reply came back, the government that sent the original message might no longer exist. You cannot build an empire when your messages take longer to deliver than your empire lasts. This is a point that Nikolai Kardashev himself acknowledged. He noted that communication from the center of the Milky Way to its edge would take about 50,000 years. At that timescale, the concept of a unified galactic civilization begins to dissolve. What you would have instead is a collection of isolated colonies, each one developing independently, each one as alone as if the others did not exist. And between those colonies, the same old problems, the same vast distances, the same limited speed of information, the same creeping expansion of space, the same radiation, the same tyranny of the rocket equation, the same fragility of biological and even technological systems over the timescales required. A civilization 1 billion years old would not be a galactic empire. It would be a scattered archipelago of independent communities, each one looking out at the same stars, each one wondering if anyone else is out there, each one unable to confirm or deny the existence of the others. This is the cosmic prison, not a prison of walls, but a prison of distance, a prison where the sentence is not confinement but separation, where the punishment is not pain but silence, where the jailer is not a tyrant but the universe itself, beautiful and indifferent and absolutely final in its judgment. And here is what makes this truly remarkable. The prison is the same for everyone. It does not matter if you are a human being or an alien from a planet orbiting a star in the Andromeda galaxy. It does not matter if your civilization is 10 years old or 10 billion years old. The rules are the same. The speed of light is the same. The expansion of space is the same. The inverse square law is the same. The cosmic microwave background is the same. The laws of physics, as far as we can tell, are uniform throughout the observable universe. The same equations that describe the behavior of matter and energy here on Earth also describe it at the edge of the cosmos. This means that if there are aliens out there, they face exactly the same challenges we do. They cannot travel faster than light. They cannot cross the cosmic event horizon. They cannot escape the expansion of space. They cannot communicate faster than their signals can travel, which is at best the speed of light. They are as trapped in their corner of the universe as we are in ours. It is a humbling thought. We sometimes imagine aliens as godlike beings, free from the constraints that bind us. But the constraints that bind us are not human constraints. They are universal constraints. They are woven into the fabric of space-time itself, and no amount of intelligence or technology can undo them. An alien civilization might be able to do amazing things within its own neighborhood, just as we can do amazing things within ours. But the neighborhood is the limit. The edge of the block is the edge of the world. And so, the silence in the sky begins to make sense, not as a sign of loneliness, but as a consequence of the universe's design. The universe is not silent because it is empty. It may be silent because it is full of civilizations that can never reach each other. Each one is a candle, burning in its own room, unable to see or be seen by the candles in other rooms. The walls between them are not walls of stone or steel. They are walls of light years and expanding space and the cold, implacable speed of causality. We are not alone because we are special. We may be alone because everyone is alone. The prison is universal, the isolation is cosmic, and the sentence is forever. Now, before we go further, let me address something that might be on your mind. You might be thinking, but what about quantum mechanics? What about entanglement? Haven't scientists shown that particles can be linked across vast distances, communicating instantly? This is a common misconception, and it is worth taking a moment to clear it up. Quantum entanglement is real. It has been demonstrated in laboratories many times. When two particles are entangled, measuring the state of one instantly determines the state of the other, no matter how far apart they are. This seems, on the surface, like it violates the speed of light. It seems like information is being transmitted instantaneously, but it is not. This is the crucial point. When you measure one entangled particle, you get a random result. It is truly random, not predictable in any way. The other particle, far away, will have the corresponding result. But because the result is random, you cannot use this to send a message. You cannot choose what the measurement will be. You can only observe what it turns out to be. And without being able to choose, you cannot encode information. The correlation is real, but it is useless for communication. This has been proven mathematically in something called the no communication theorem, which shows that quantum entanglement by itself cannot be used to send information faster than light. Every attempt to find a loophole has failed. The universe is extraordinarily good at protecting its speed limit, even in the strangest corners of quantum physics. So no, quantum mechanics will not save us from the cosmic prison. Neither will any other branch of physics that we currently understand. The prison is real, the walls are real, and they are made of the most fundamental rules that the universe has. Let me tell you about something that happened in 1977, the same year Voyager 1 was launched. A signal was detected by the Big Ear radio telescope at Ohio State University. It was a burst of radio energy that lasted 72 seconds. It was strong, narrowband, and it came from a direction in the sky near the constellation Sagittarius. The astronomer who spotted it in the printout was so surprised that he circled it and wrote the word "wow" in the margin. It has been known as the wow signal ever since. For decades, the WOW signal was considered the best candidate for an extraterrestrial transmission. It had many of the characteristics that SETI scientists look for in an alien signal. It was narrowband, meaning it occupied a very specific frequency range, which is unusual for natural sources. It was strong, standing out clearly from the background noise, and it came from a direction in the sky where no known natural source could explain it. But it was never detected again. Despite repeated attempts to observe the same spot in the sky, using the same frequency and the same equipment and later equipment that was far more sensitive, the signal never reappeared. It was a one-time event, a single burst, and without a repeat, there was no way to confirm what it was. In 2022, a team of researchers proposed that the WOW signal might have been caused by a naturally occurring astronomical phenomenon, specifically the interaction between a hydrogen cloud and a specific type of master emission in interstellar space. This explanation is still debated, but it illustrates a broader point. Even when we think we might have found something, the universe has a way of reminding us that natural phenomena can mimic the signatures of intelligence. The cosmos is full of strange and unexpected events, and distinguishing an alien signal from a natural one is enormously difficult. The WOW signal is a perfect metaphor for our situation, a brief, tantalizing glimpse of something that might be extraordinary, a moment of hope and excitement, and then silence. Decades of silence, the sky offering nothing else. Just the hum of the cosmic microwave background, the crackle of distant quasars, and the steady, empty whisper of a universe that has nothing to say to us. Or, perhaps more accurately, a universe that has everything to say but no way to be heard. There is another layer to the biology problem that we touched on, but did not fully explore. It is the question of what happens to the mind, not just the body, during a journey that lasts decades or centuries. We know what isolation does to people. Studies of Antarctic winter over crews, submarine crews, and astronauts have shown that prolonged isolation and confinement can lead to depression, anxiety, interpersonal conflict, cognitive decline, and a condition sometimes called third quarter syndrome, where motivation and morale drop sharply about 3/4 of the way through a long mission. On the International Space Station, astronauts can look out the window and see Earth. They can talk to their families in real time or close to it. They know that rescue is possible. They know that home is just a few hundred kilometers away. And even with all of those comforts, the psychological effects of long-duration spaceflight are significant. Now imagine a crew on an interstellar vessel, years into the journey. The sun is just another star among millions. Earth is invisible. Communication with home takes months or years because of the speed of light delay. There is no possibility of rescue, no possibility of turning back. The destination is so far away that it might take generations to reach. The crew would spend their entire lives in a metal can, surrounded by the same faces, the same walls, the same recycled air, with nothing outside the windows but the cold, unchanging void. The psychological toll of such a journey would be immense. Humans are social animals. We need variety, novelty, nature, community, purpose, and the feeling of being connected to something larger than ourselves. A generation ship might try to provide some of these things through artificial environments, gardens, social structures, and education. But it could never replicate the richness and unpredictability of life on a planet. It could never offer the simple joy of walking through a forest or swimming in an ocean, or watching a sunset paint the sky in colors you have never seen before. Some scientists have speculated that the crew of a generation ship would inevitably develop psychological and social problems that could threaten the mission. Hierarchies might form. Power struggles might erupt. Knowledge might be lost between generations if the educational system breaks down. The original purpose of the mission might be forgotten or rejected by descendants who never chose to be born on a ship in the middle of nowhere. Science fiction often portrays generation ships as romantic adventures, but the reality would likely be closer to a prison sentence. A very long, very uncomfortable prison sentence, served by people who committed no crime, in a vessel they cannot leave, heading toward a destination they may never reach. And even if the psychological problems could be managed, there is the question of genetic diversity. A viable human population on a generation ship would need to be large enough to avoid the problems of inbreeding. Scientists have estimated that a minimum viable population for a multi-generational space journey would be in the hundreds, possibly the thousands. Each person would need food, water, air, living space, medical care, education, and meaningful work. The ship would need to be enormous. The infrastructure would need to be flawless. A single critical failure, a crop blight, a water recycling breakdown, a hull breach, could doom the entire mission. We are not good at building things that last for centuries without maintenance. Our longest lasting structures on Earth, the pyramids, the Roman aqueducts, the Great Wall, required constant human intervention to survive, and they were built on a planet with breathable air, stable temperatures, abundant water, and no cosmic rays. A generation ship would need to be maintained in an environment that is actively hostile to its existence for periods of time that exceed the lifespan of any technology we have ever built. The engineering alone is daunting, but the biology, the psychology, and the sociology are even harder, because you are not just building a machine, you are building a world, a self-sustaining, self-governing, self-repairing world that has to work perfectly for hundreds of years. And we have never, in the entire history of our species, managed to build a society that was stable for that long. Empires rise and fall. Civilizations collapse. Technologies are invented and forgotten. The idea that we could build a perfect, self-sustaining society in a metal tube and send it across the galaxy is, to put it gently, optimistic. Let me also talk about something that gets overlooked in discussions of interstellar travel: the problem of navigating. At first, this might seem like a minor issue. You know where you want to go. You point the ship in that direction. You accelerate. You wait. But space is not static. Stars move. The Sun, for example, orbits the center of the Milky Way at about 220 kilometers per second. It completes one orbit every 225 million years or so. And every other star in the galaxy is doing the same thing, each one on its own orbit, at its own speed, in its own direction. A star that is 4 light years away from us now will not be 4 light years away in 1,000 years. It will have moved. Not by a lot, relative to the galaxy as a whole, but by enough to matter if you are trying to aim a spacecraft at it. Over the course of a multi-thousand-year journey, the target star could have shifted significantly from its initial position. The ship would need to adjust its course, which requires fuel, which requires more mass, which brings us back to the tyranny of the rocket equation. And navigating in interstellar space is not like navigating on Earth, where you have landmarks and GPS satellites and maps. In the void between stars, there are no landmarks. There is just darkness and the distant points of stars, which all look different from different angles. A ship traveling at a significant fraction of light speed would also experience aberration, a relativistic effect that distorts the apparent positions of stars depending on the direction and speed of travel. Forward-facing stars would appear to cluster together and shift toward blue frequencies. Rearward-facing stars would spread apart and shift toward red. The familiar sky would become unrecognizable. Navigation at interstellar speeds would require extraordinarily precise instruments and sophisticated computer algorithms. The ship would need to continuously track the positions of multiple reference stars, correct for relativistic effects, account for the motion of its target, and adjust its course accordingly. All of this while moving through a medium that is constantly bombarding it with radiation and micrometeorites. It is doable, in principle, but it adds yet another layer of complexity to a problem that is already overwhelming. Let me also revisit the question of propulsion, because there is one more aspect of it that deserves attention. When we talk about accelerating a spacecraft to a significant fraction of the speed of light, we usually focus on the energy required to speed it up, but we often forget about slowing it down. If you are doing a flyby, just passing through a star system without stopping, then you do not need to decelerate. But a flyby at 10% of the speed of light would give you only a few hours in the target system, not nearly enough time to study anything in detail, let alone land on a planet or make contact with a civilization. If you want to actually stop at your destination, you need to decelerate. And deceleration requires exactly the same amount of energy as acceleration, which means the total energy budget for the trip doubles. And because of the rocket equation, the fuel required for deceleration must be carried from the start, which means you need even more fuel for acceleration, which means even more fuel for that fuel, and the numbers spiral upward rapidly. Some proposals have suggested using the destination star's light or magnetic field for braking, or deploying a magnetic sail that interacts with the interstellar medium. These are creative ideas, but they are untested and may not work at the speeds required for practical interstellar travel. The bottom line is that getting somewhere fast and stopping when you arrive are two separate engineering miracles, and both of them have to work perfectly for the mission to succeed. A ship that runs out of fuel halfway through deceleration would shoot past its target at thousands of kilometers per second, unable to stop, unable to turn around, doomed to coast through the void forever. There is something almost poetic about that image. A ship that crossed the void, that survived the radiation and the cold and the centuries of loneliness, only to miss its destination by a cosmic hair and drift on into the darkness forever. Let me also mention one more challenge that applies not just to physical travel, but to any attempt at interstellar contact. It is the problem of recognizing intelligence. We tend to assume that if aliens exist, they would communicate in ways we could understand. Radio signals, laser beams, mathematical patterns. But that assumption is deeply rooted in our own cognitive biases. An alien intelligence might process information in ways so different from ours that we would not recognize their signals as signals at all. They might use modalities we have not thought to look for. They might encode information in patterns so foreign to our thinking that they would look like noise to our instruments. We have enough trouble understanding the communication systems of other species on our own planet. Whale songs, dolphin clicks, the chemical signals of ant colonies. These are intelligent communication systems produced by brains that evolved on the same planet as ours, under the same physical conditions, using the same biochemistry, and we still do not fully understand them. How much harder would it be to understand a signal produced by a completely alien intelligence, one that evolved under different conditions, with different senses, different chemistry, and different cognitive architecture? The answer is that it might be impossibly hard. We might receive a signal from an alien civilization and not even know it. We might dismiss it as natural noise. We might catalogue it as an interesting astronomical phenomenon and move on. The universe might be full of messages that we are simply not equipped to read. This is a humbling thought. It suggests that even the act of listening, which seems like the simplest and most passive approach to the problem, is fraught with assumptions and limitations. We are not just limited by the speed of light and the expansion of space. We are limited by the boundaries of our own minds, our own sensory systems, our own cognitive frameworks. We are looking for something we might not recognize even if we found it. And so the silence deepens. Not just the silence of empty space, but the silence of incomprehension. The silence of two beings shouting at each other in languages neither one can hear. The silence of a universe that may be rich with meaning, but beyond our ability to decode. This is, perhaps, the deepest layer of the cosmic prison. Not just the walls of physics, not just the bars of biology, but the windows of perception through which we can only see a fraction of what is actually there. The universe is not just too big to cross, it is too strange to fully understand. And in that strangeness, in that irreducible mystery, there may be answers to questions we have not yet learned to ask. But even with all of these unknowns, there is one thing we do know. We know the rules of the game, even if we do not know all the players. We know the speed of light. We know the expansion rate. We know the energy equations. We know the radiation environment. We know what microgravity does to bones. We know the inverse square law. We know the rocket equation. And every single one of these known quantities points in the same direction. The stars are beautiful. They are fascinating. They are, for a thinking being, irresistible. But they are not for visiting. They are for admiring. They are for studying. They are for wondering about. They are candles in windows we will never open. Lights at the end of corridors we will never walk. And in the end, that might be the most important thing the universe has to teach us. Not how to cross the void, but how to live with it. How to find meaning and beauty and purpose in a cosmos that does not offer shortcuts or easy answers. How to be small and still matter. How to be brief and still be significant. How to look at something infinite and unreachable and still feel, in the very core of your being, a connection to it. Because the connection is real. It is not made of spaceships or radio signals. It is made of physics. The same physics that prevents us from traveling to the stars also connects us to them. The same atoms that make up your body were forged in stellar furnaces billions of years ago. The same forces that hold galaxies together hold your cells together. The same light that crosses the void between stars crosses the space between the photons entering your eyes and the neurons firing in your brain. You are not separate from the universe. You are a part of it. A tiny, conscious, wondering part. And that is the most extraordinary thing in the cosmos. So where does all of this leave us? We have walked through the physics. We have looked at the biology. We have measured the distances and counted the energy and listened to the silence. And the answer, the honest answer, is that the stars are almost certainly out of reach. Not just for us, for everyone. But I want you to sit with that for a moment. Not because it should make you sad, although it might, but because there is something in this answer that is, I think, deeply and unexpectedly beautiful. We live in a culture that worships expansion. We celebrate growth, exploration, conquest, the relentless pushing of boundaries. And there is something wonderful about that instinct. It built our cities. It explored our oceans. It sent us to the moon. But there is another side to it, a shadow. We sometimes treat the idea of limits as a failure, as if the universe owes us infinity, as if the fact that there is a wall somewhere ahead of us is a defect in reality that needs to be fixed. But what if the wall is not a defect? What if it is the point? Think about what makes a moment precious. It is not its length, it is its scarcity. A sunset is beautiful precisely because it ends. A conversation with someone you love is meaningful precisely because it will not last forever. A life is valuable precisely because it is finite. If sunsets lasted forever, we would stop watching them. If conversations never ended, we would stop listening. If life went on without limit, we would stop caring. The universe, for all its vastness, is telling us the same thing. It is telling us that this moment, this place, this tiny pale blue dot spinning around an ordinary star in an ordinary galaxy, is precious. Not because it is special in the cosmic scheme of things, not because it is the center of anything, but because it is ours, and it is the only one we will ever have. The impossibility of interstellar travel does not make the universe smaller. It makes this planet more important. It makes this moment more valuable. It makes every sunrise, every breath of clean air, every glass of water, every conversation with a friend more remarkable than we usually give it credit for. Because there is no backup. There is no colony on Alpha Centauri waiting for us if we ruin this. There is no escape pod to another star system. There is no Galactic Federation coming to rescue us. We are on our own, on this island, in this ocean, under these stars. And that is not a tragedy. That is a responsibility. And it might also be the most beautiful thing about being alive. I think about the astronauts who have looked at Earth from space, who have described what is called the overview effect, the profound emotional experience of seeing your home planet as a tiny, fragile ball hanging in the darkness. They come back changed. They talk about the thinness of the atmosphere, the fragility of the biosphere, the absurdity of borders and wars and petty conflicts when seen from that altitude. They see the Earth for what it truly is, a small, vulnerable oasis in an ocean of nothing. Now multiply that feeling by the scale we have been discussing tonight. Not just the thinness of the atmosphere, but the vastness of the space beyond it. Not just the fragility of the biosphere, but the impossibility of ever reaching another one. The Earth is not just our home. It is our only possible home. The one and only lifeboat in an ocean that stretches to infinity. And everything we will ever do, everything we will ever build, every relationship we will ever have, every discovery we will ever make will happen here, or not at all. That is both terrifying and magnificent. It concentrates everything. It distills the entire meaning of our existence into a single point. Here, now, this. Let me tell you something else about the universe that I find strangely comforting. The same physics that keeps us here, that prevents us from reaching the stars, is also the physics that made us possible. The speed of light, the expansion of space, the fundamental constants of nature, these are not arbitrary values. They are finely tuned in a way that physicists still do not fully understand to allow complex structures to exist. If the speed of light were different, atoms would not form. If the expansion rate were different, galaxies would not coalesce. If the strength of gravity were slightly different, stars would burn too fast or not at all. If the strong nuclear force were a little weaker, hydrogen would be the only element. If it were a little stronger, all the hydrogen would have been converted to helium in the Big Bang, and there would be no water, no chemistry, no life. The universe is not hostile, it is indifferent. But within that indifference it has, through an astonishing coincidence of physical constants, created the conditions for something remarkable. For matter to organize itself into structures of breathtaking complexity, for chemistry to become biology, for biology to become consciousness, for consciousness to look up at the sky and ask, is anyone else out there? The answer, as far as we can tell, is that we do not know, and we may never know. The distances are too great, the signals are too faint, the timescales are too long, but the question itself, the very fact that we can ask it, is extraordinary. We are the universe asking about itself. We are matter that has arranged itself into a pattern complex enough to wonder about its own existence. That is not a small thing. That is the most remarkable thing that has ever happened, as far as we know, anywhere in the cosmos. And it happened here, on this tiny planet, orbiting this ordinary star, in the suburbs of this spiral galaxy, in this unremarkable corner of the observable universe. Out of all the atoms in all the stars, in all the galaxies, in all the billions of light years of space, some of those atoms are here, right now, arranged in the specific pattern that is you, listening to these words, thinking these thoughts, wondering about the stars. You are made of the same stuff as the stars. The carbon in your cells was forged in the core of a massive star that exploded billions of years ago. The iron in your blood was created in a supernova. The calcium in your bones, the oxygen in your lungs, the nitrogen in your DNA, all of it was made in stars, scattered across space, collected into a planet, organized by chemistry and time into the extraordinary machine that is your body. You are, in the most literal sense, stardust. You are the cosmos looking at itself, and that cosmos, for all its vastness, for all its distances, for all its silence, created you. It created this moment. It created the night sky, and the questions, and the longing, and the wonder. It did not create a way for you to visit the other stars, but it created you to look at them and feel something. And maybe that is enough. Let me take you on one more journey before we go. Let me take you to the furthest reaches of the observable universe, to the very edge of what we can see. Imagine you are in a spacecraft, not a real one, bound by fuel and physics, but an imaginary one, a ship of pure thought that can cover any distance in an instant. You start at Earth. You pull away from the surface, past the clouds, past the satellites, past the moon. You sweep past Mars, past the asteroid belt, past the giant planets with their swirling storms and their frozen moons. You reach the outer solar system, where Pluto drifts in the cold, where the Kuiper belt is a ring of icy bodies circling the sun like a distant halo. You keep going, past the heliopause, where the solar wind meets the interstellar medium. Past the Oort cloud, a vast spherical shell of comets at the very edge of the sun's gravitational influence. It takes Voyager 1 decades to cross this region. In your imaginary ship, it takes moments. Now you are in interstellar space, true interstellar space, the darkness between the stars. And it is dark. Darker than anything you have ever experienced on Earth. No streetlights, no moon, no reflected light from clouds, just the pinpoints of distant stars, each one a sun, each one potentially surrounded by planets, each one impossibly far away. You fly on, past Alpha Centauri, the nearest star, past Sirius, the brightest star in our sky, past the bright young stars of the Orion Arm, the region of the Milky Way where our sun lives. You pass through the arm and into the space between the arms, where the stars are thinner and the darkness deeper. You reach the center of the galaxy. Here, a supermassive black hole called Sagittarius A sits at the heart of a dense cluster of old stars. It has a mass of about 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury. Nothing that falls past its event horizon ever comes back. Not light, not information, not time. It is the ultimate prison, a point of no return at the center of our cosmic home. You fly on past the galactic center, through the other spiral arms, past billions of stars, past nebulae where new stars are being born from clouds of gas and dust, past the remnants of supernova where old stars have died in violent explosions. You reach the edge of the Milky Way, where the stars thin out and the darkness of intergalactic space begins. And now you see something that takes your breath away. The void between galaxies. It is vast, incomprehensibly vast. A gulf of emptiness that makes the distances between stars look like nothing. A few lonely atoms of hydrogen per cubic meter, scattered through a darkness that stretches for millions of light years. No stars, no planets, no light except the faint cold glow of the cosmic microwave background. You fly across this void to the Andromeda Galaxy. It takes 2.5 million light years to cross. In your imaginary ship, it is a moment, but in reality, it would take even a beam of light 2.5 million years, and when you arrive, you find a galaxy much like your own. Spiral arms, billions of stars, probably trillions of planets, possibly life, possibly civilizations. But all of them as isolated from the Milky Way as the Milky Way is from them. You keep going, galaxy after galaxy, cluster after cluster, supercluster after supercluster. The universe opens before you like a fractal, each level of structure revealing more of the same pattern. Filaments of galaxies separated by voids, voids within voids, structures within structures, all of it expanding, all of it growing, all of it drifting apart. You reach the edge of the observable universe, 46 billion light years from Earth. Beyond this point, light has not had time to reach us since the Big Bang. We do not know what is out there. More galaxies, probably. More voids. More of the same. Perhaps the universe goes on forever. An infinite repetition of the same pattern, stretching without end in every direction. And here, at the edge of everything we can see, you turn around and look back. And from this distance, our entire galaxy, our home, with its hundreds of billions of stars and its spiral arms and its supermassive black hole and its pale little solar system with its tiny blue planet, is invisible. Not just small, invisible. Too far away, too faint, too insignificant to register against the vast backdrop of the cosmos. That is our place in the universe. A single candle in a cathedral the size of a continent. A whisper in a storm that spans all of existence. A flicker of consciousness in an ocean of unconscious matter and energy and space and time. And yet, that candle is burning. That whisper is real. That flicker of consciousness is you and me, and everyone who has ever lived and loved and wondered about the stars. The universe may be vast and silent and indifferent, but it made us, and through us it knows itself. Let us come back now. Let us return to Earth. Let us leave the edge of the observable universe and fly back through the galaxy clusters and the voids and the spiral arms and the interstellar darkness. Let us pass Alpha Centauri and the Oort cloud and the outer planets and the asteroid belt and Mars. Let us come home, because this is home, this small world, this thin atmosphere, this warm ocean, these green forests and white clouds and brown deserts. This place where, against all the odds, matter has organized itself into life, and life has organized itself into consciousness, and consciousness has looked up at the sky and asked the biggest questions there are. We cannot reach the stars. That is what the physics says. We cannot send ships across the void. We cannot receive messages from civilizations that may or may not exist. We are, for all practical purposes, alone. Not because the universe is empty, but because it is too big, too old, too fast, and too indifferent to allow its scattered children to find each other. But we are here, right now, on this extraordinary planet, breathing this extraordinary air, looking at these extraordinary stars, and the very fact that we can understand why we cannot reach them is, in itself, a kind of miracle. Think about it. The universe is made of atoms, and some of those atoms are arranged in a pattern that can understand the universe. The same physics that keeps us trapped here also built the brains that can comprehend the trap. The same expansion that is pushing the galaxies apart also created the conditions for galaxies to form in the first place. The same speed of light that limits our reach also carries the images of distant worlds to our telescopes. The prison is also the palace. The wall is also the window. The silence is also the song. We are not the masters of the universe. We are its witnesses. And maybe, in the end, that is more important. When the last galaxy fades beyond the event horizon, when the last star burns out, when the universe drifts into its final cold darkness, what will matter is not how far we traveled. It will be what we understood, what we felt, what we created with the time and the space and the light that were given to us. And we have been given quite a lot. A planet that is almost impossibly beautiful. A sky full of stars that, even if we cannot visit them, we can study and admire and love from afar. A civilization that, for all its flaws, has produced music and art and science and philosophy and compassion and curiosity and wonder. A moment in cosmic history that is brief and precious and unrepeatable. That is not nothing. That is everything. There is a concept in Japanese aesthetics called mono no aware. It is usually translated as the pathos of things, or the bittersweet awareness of impermanence. It is the feeling you get when you watch cherry blossoms fall, knowing they will not last. The feeling you get when you hear a beautiful piece of music and know it will end. The feeling you get when you hold someone's hand and know that someday, inevitably, you will have to let go. The universe is full of mono no aware. Every star will eventually burn out. Every galaxy will eventually drift beyond the cosmic event horizon. Every planet will eventually grow cold. Every living thing will eventually die. Nothing lasts. Nothing is permanent. Nothing endures. But that is precisely what makes it all so beautiful. The cherry blossoms are lovely because they fall. The music is moving because it ends. The hand in yours is warm because you know it will not always be there. And the stars are magnificent because they are beyond our reach. If we could hop between stars like stepping stones across a creek, the universe would lose its grandeur. If we could visit any planet, meet any civilization, cross any void, the cosmos would become mundane. It is the distance, the impossibility, the sheer unreachable vastness of it all that gives the night sky its power. When you look up at the stars, you are looking at something you can never touch. And that untouchability, that infinite separation between your eyes and the light they are receiving, is what makes the moment so achingly beautiful. We spend so much time trying to conquer the universe that we forget to be amazed by it. We forget that amazement is its own reward. We forget that the feeling of wonder, the gasp that escapes your lips when you see a photograph from the James Webb Space Telescope, the shiver that runs down your spine when you learn that the light from a distant galaxy has been traveling for billions of years, that feeling is the point. The universe did not make us to cross it. It made us to see it, to understand it, to marvel at it, and to tell each other about it, in stories and equations and songs. Let me share a few more things about the universe that I think are worth knowing. Not because they change the conclusion we have reached tonight, but because they add texture to it. They deepen the picture. They make the prison more intricate and more wonderful. Did you know that in the deep space between stars, the temperature is just a few degrees above absolute zero? Absolute zero is the coldest anything can be, the point where all molecular motion stops. It is about minus 273 degrees Celsius. The void between stars is not quite that cold, because the cosmic microwave background warms everything in the universe to about 2.7 degrees above absolute zero. But it is close. So close that any unprotected human would die of hypothermia in minutes. So close that water would freeze instantly and metal would become brittle and shatter. This is the environment that any interstellar traveler would have to endure, not for hours or days, but for years, decades, centuries. A cold so profound that it defies human experience. A darkness so complete that the only light comes from the distant pinpoints of stars, each one a reminder of how far away everything is. Did you know that space is not truly empty? Even in the voids between stars, there are a few atoms per cubic centimeter. Most of them are hydrogen, the simplest and most abundant element in the universe. Some are helium, left over from the Big Bang, and a tiny fraction are heavier elements, scattered by the explosions of ancient stars. These atoms are so sparse that they barely interact with each other. If you could somehow stand in the interstellar medium, it would feel like a vacuum. Your lungs would find nothing to breathe. Your body would find nothing to push against. But over vast distances, even these sparse atoms add up. A ship traveling at a significant fraction of the speed of light would slam into them like a car driving through rain. At 10% of the speed of light, each hydrogen atom that the ship encountered would strike its hull with the energy of a tiny bullet. Over time, the cumulative effect would be like a sandblaster eroding the leading surfaces of the ship, creating a stream of secondary radiation and adding to the already enormous radiation problem we discussed earlier. Some engineers have proposed magnetic or electrostatic shields at the front of a spacecraft to deflect these interstellar atoms. This is theoretically possible, but it would require enormous amounts of energy and would add significant complexity to an already impossibly complex machine. And at higher speeds, closer to the speed of light, the problem becomes dramatically worse. At 90% of light speed, each hydrogen atom would carry the energy of a cosmic ray. The ship would essentially be flying through a radiation field of its own creation. Did you know that the Milky Way is on a collision course with the Andromeda Galaxy? In about 4.5 billion years, the two galaxies will begin to merge. This is not as violent as it sounds, because the spaces between stars are so vast that very few individual stars will actually collide. But the gravitational interaction will tear apart the spiral arms of both galaxies, flinging stars into new orbits, creating tidal tails of debris stretching millions of light years into space, and eventually merging the two galaxies into a single, enormous elliptical galaxy that astronomers have already named Milkomeda. This event will be spectacular, but it will also be another reminder of the impermanence of everything. The Milky Way, our cosmic home, is not eternal. It will be transformed, absorbed, remade into something new. The stars we see tonight will be scattered. The constellations will change beyond recognition. Even the night sky itself, the canvas that has inspired every civilization in human history, will be different. And through all of this, the expansion of the universe will continue. The other galaxy clusters, the ones beyond our local group, will keep receding. The event horizon will keep closing. The observable universe will keep shrinking. And in the very, very far future, trillions of years from now, the only thing left within reach will be whatever remains of Milkomeda, slowly cooling, slowly fading, its stars burning out one by one, until even the last red dwarfs flicker and go dark. This is the future of the universe as we understand it, not with a bang, but with a long, slow, quiet fade to black. The cosmologists call it the heat death, the point where all energy has been evenly distributed and no more work can be done. No more stars, no more light, no more change. Just an infinite expanse of cold, dark, motionless matter, drifting through a space that continues to expand forever. It is a melancholy picture, but there is something peaceful about it too. The universe had its moment. It burned bright and hot and full of possibility. It created stars and galaxies and planets and, in at least one place, life. It looked at itself through the eyes of creatures it had built from its own substance. And then, having done all of that, it rested. Like a fire that has burned through all its fuel, it settled into embers, and then into ash, and then into stillness. We are in the burning phase right now. The universe is still making new stars, still forming new galaxies, still capable of producing the conditions for life. We live in the golden age of the cosmos, the period when the most interesting things are still happening. In a few billion years, star formation will begin to slow. In a few trillion years, it will stop entirely. We are lucky to be here now, in this brief window when the universe is alive with possibility. And that brings me back to the question of aliens, because if we are living in the golden age of the cosmos, then so is everyone else. Any civilization that exists right now, anywhere in the universe, is living in the same window of opportunity. They have the same stars, the same planets, the same chemistry, the same physics. They face the same challenges and the same limits. And they are also facing the same clock. The universe will not be habitable forever. The stars will not burn forever. The conditions for life will not persist forever. Whatever civilizations exist out there, they, like us, are temporary. They are sparks in the darkness, flickering for a moment, and then fading. This shared transience connects us, even if we can never meet. We are all in the same boat, even if we are in different oceans. We are all looking at the same stars, even if we see them from different angles. We are all asking the same questions, even if we use different words. And we are all facing the same answer, which is that the universe is wonderful and vast and temporary, and our job is not to conquer it, but to appreciate it while we can. I sometimes wonder what an alien civilization would think if they understood what we understand. If they looked at the same physics, the same expansion, the same cosmic event horizon, and came to the same conclusions. Would they be sad? Would they be angry? Would they shake their fists, or whatever they have, at the sky and curse the speed of light? Or would they do what I think the wisest among us do? Would they look around at their own world, their own sky, their own community, and realize that what they have is enough? That the fact of being alive, of being aware, of being able to ask the question at all, is a gift so extraordinary that it does not need anything else to complete it. I like to think they would. I like to think that somewhere, on a planet orbiting a star we have never seen, there is a being looking up at a sky full of unreachable, stars, and feeling the same mix of wonder and sadness and gratitude that you might be feeling right now. I like to think that the universe, in its own quiet way, is full of creatures staring at the same walls and finding the same beauty in them. We will never meet them. We will never hear their songs or read their stories or learn their names, but we share something with them that is deeper than communication. We share the experience of being conscious in a universe that did not have to make us but did. We share the experience of looking up and wondering. We share the experience of being alive. And that, in the end, is the real message of the cosmic silence. It is not a message of loneliness. It is a message of solidarity. We are all in this together, even if together means impossibly apart. We are all part of the same story, even if we can never compare notes. We are all children of the same universe, born from the same atoms, bound by the same laws, and facing the same beautiful, terrible, magnificent reality. The stars are not ours to visit. They are ours to love from a distance. So the next time you look up at the night sky, do not think of it as a map of places you cannot go. Think of it as a portrait of the universe that made you. Every star you see contributed in some way to the atoms in your body. Every galaxy you glimpse is a cousin, a distant relative in the great family of cosmic structures. The light that enters your eyes has traveled for years, decades, centuries, millennia to reach you. It has crossed the void, survived the expansion, endured the cold and the dark, just to end its journey on the retina of a being that can appreciate what it has been through. That is not nothing. That is a cosmic love story, a story told in photons and light years and billions of years of patient travel. A story that connects you personally to the farthest reaches of the observable universe. You are made of stars. You are lit by stars. You are connected to stars by the very light that you see. And if you cannot visit them, well, perhaps that is all right. Perhaps it is enough to know that they are there, that they are burning, that they are making the heavy elements that will someday, somewhere, become the building blocks of something new. Perhaps it is enough to know that the universe, for all its vastness and silence, is not empty. It is full of matter and energy and light and time, full of potential, full of the possibility that somewhere, on some distant world, around some unimaginable star, something is looking up and wondering the same things you are wondering right now. We are drifting, all of us, through a universe that is drifting too. The galaxies are drifting apart. The stars are drifting through the arms of the galaxy. The planets are drifting around their stars. And we, on this small world, are drifting through our lives, one day at a time, one moment at a time, one breath at a time. The drift is not a failure. It is the motion of the universe. It is the way things work. It is the gentle, ceaseless movement of everything that exists, from the largest galaxy cluster to the smallest atom, all of it in motion, all of it changing, all of it flowing forward through time toward an unknown destination. And the beauty of it is that while we drift, we are awake, we are aware, we are here right now in this extraordinary moment in cosmic history, on this extraordinary planet, under this extraordinary sky. We are the universe's way of experiencing itself. We are the cosmos, conscious. And for as long as we are here, the universe is not silent. It is singing, quietly, gently, in the language of physics and chemistry and biology and consciousness, a song that no one else may ever hear, but that is no less real for its loneliness. I want to leave you with one last thought. It is about a photograph taken in 1990 by the Voyager 1 spacecraft from a distance of about 6 billion kilometers. Carl Sagan had persuaded NASA to turn the cameras around and take a picture of Earth from the outer solar system. What they captured was a tiny pale blue dot, smaller than a single pixel, suspended in a beam of sunlight. Sagan wrote about that photograph. He said, "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." He went on to talk about the folly of our conceits. The rivers of blood spilled so that one group could rule, a fraction of that dot, the cruelties and tragedies and triumphs and joys of every human life, all played out on a stage the size of a mote of dust, suspended in a sunbeam. That photograph is what the universe looks like from just the edge of our own solar system. From the nearest star, the Earth would be invisible. From the nearest galaxy, the Sun would be invisible. From the edge of the observable universe, nothing about us would be detectable at all. We are infinitely small in an infinitely large cosmos, and yet here we are, thinking, feeling, wondering, creating, loving, looking up at the stars and asking the biggest questions there are. That is the real miracle. Not that we might someday reach the stars, but that we exist at all. That the universe, in its unfathomable complexity, produced beings capable of understanding their own limitations. Beings who can look at the night sky and know with mathematical certainty that they will never touch what they see, and who can still find beauty in the looking. The universe will not deliver aliens to our doorstep. The distances are too great. The speeds are too slow. The expansion is too fast. The energy is too scarce. The biology is too fragile. The signals are too faint. The silence is real, and it is probably permanent. But the universe did deliver something. It delivered you. It delivered this moment. It delivered this planet, with its oceans and forests and mountains and skies. It delivered the ability to see, to think, to feel, to wonder. And it delivered the stars themselves, burning their ancient light into the darkness, asking nothing, offering everything, simply by being there. That is enough, more than enough. It is everything. So wherever you are listening from tonight, in whatever corner of this vast, quiet world you call home, take a moment, look up if you can, or just close your eyes and picture the sky. The stars are there even if you cannot see them. They are burning for no one in particular. Their light is traveling in all directions, reaching everything and no one. It has been doing this for billions of years. It will continue for billions more. And some of that light, a tiny fraction of it, is falling on you. Right now, in this moment, connecting you to something immeasurably old and impossibly far away. You cannot reach it, but it has reached you. That is the story of the cosmos, not a story of conquest and exploration, but a story of light traveling through darkness, reaching out across the void, finding, every once in a while, something alive enough to notice. You are that something, and the universe, in its own slow, patient, beautiful way, is grateful. Thank you for drifting with me tonight. If you are still awake, I hope the sky looks a little different to you now, a little more vast, a little more quiet, a little more precious. If you enjoyed this journey through the cosmos, consider subscribing to Cosmic Drift. We explore the universe together, one quiet night at a time. And if you have a moment, I would love to know, where in this vast, quiet world are you listening from tonight? If you made it here, you already know what this feels like, that quiet, that drift. But every night it ends. The video stops. The silence wakes you. and you're reaching for your phone at 3 a.m., choosing something new when all you wanted was to stay asleep. Beyond the Stars was made for that moment. 5 deep sleep experiences, hours long, no ads, no endings, just the night, all the way through. Yours tonight for a one-time purchase. Begin now at mycosmicdrift.com.